Hello and welcome to another episode of the Closure Peels screencast. This is episode number 6. We're going to see a function called Memoize from the standard library. Before we start, as usual, the content of the screencast is based on the book I'm writing. That is a book by Manning. That is the link to the website of the book. So if you enjoy this screencast, you might also enjoy the content of this book. The screencast is just a summary of what is in the book that is much more extended in terms of examples, tables, and other interesting information that I cannot cover completely in the screencast. That is my Twitter handle, @reborg, if you want to get in touch. Memoize is an interesting function because it gives you a very basic caching capability built into the standard library. So it is used not very frequently, and the reason for the being used very frequently is because it is not really flexible. So it's caching, it's probably producing better performance in certain cases, but it doesn't have any strategies like LRU, last recently used, or like eviction policies like other modern libraries. So this limits the use of the internal Memoize to a few cases. But still, it's good to have it in the standard library tools, and it's good to use it sometimes. How does it work? So I'm going to try a slightly different way of showing you code this time. I'm using a screen split in two horizontal windows, and I have pre-written code at the top that I'm going just to evaluate and comment at the bottom. This is because, especially for this episode, there was a lot of code to write, and writing it in real time is not, it can be a long process. So let's say we have this function called busy. It's taking two arguments and it's printing line busy with these two arguments and summing them up. Very easy function. If you try a REPL, you will see that it's printing both the result and the print line. If we memoize it, and it's as easy as just invoking memoize on the function, so memoize takes a function as argument and returns another function as output. The function that Memoize returns is a decoration of the inner function or target function, in this case the function busy, and the decoration is basically inspecting the arguments and using them as a key into a hash map, and whenever that key is present in the hash map, instead of invoking the function again, it's just returning the results that are cached in the map. So if we try again our new busy memo function with 3 and 2, we can see that it prints busy 3 and 2, but if we run it again, run it twice, the print line disappears, and this is because the result 5 was cached, but the side effect, the print line, was not, and so if we try again, we don't see it appearing again. So how or when we can use Memoize? So there are several scenarios. One that I want to show you today is is an example that is representative of the kind of context where Memoize is a good choice. And the context is like computationally intensive functions where you can control the key space. So you have an idea of how the function is going to be invoked at runtime, and you can sort of control that. And by control, I mean the key space is not completely random, but is some enumerable set that is not infinite. And that is because then you can effectively cache some of those calls in an effective way with Memoize. And this is like a power set, the definition of a power set. And a power set is just the set of all the subsets of a set. And to explain how it works, we have an example here. So if we take 1, 2, and 3, 1, 2, and 3 as a set, then we can have 8 possibilities, 8 subsets, including 2 special subsets. And one is the set itself, 1, 2, 3, and the one is the empty set. And all the other combinations of 1, 2, and 3 taken in such a way that each subset is not overlapping with any other. So they are all distinct subsets. There are 2 to the power of 3. So more in general, there are 2 to the power of n subsets, and in the definition of power set. So what we can probably already intuitively show here is that this is an expensive operation that grows exponentially quite fast. And it's also a good operation for Memoize because there are many intermediate results that we can cache, and we don't need to replicate. We don't need to execute again at each invocation. So in this diagram, I want to show you one algorithm that we can use to find all the subsets of a set. And there might be others, but this one is very concise and clear to explain and clear to see. So we have on the left side the call going down deep inside the stack, so it will be a recursive algorithm, and on the right side we are going back up the stack to show what happens when we go back. So we start, for example, with a set of A, B, C, and D keywords. So in order to find the subsets, the general rule that we can apply is to take the first of these elements, let's say A, and insert A into each of the power set, and this is the recursion, of the remaining elements of the set, so B, C, and D. And if we do this, then we go to the second of the circles on the left, and we insert instead B into each of the remaining C and D. And we repeat this until we arrive at some point where we don't have any more elements to insert. So that is the bottom of this picture. Insert D into each of the empty set. So we don't have anything remaining. So when we do that, you can see on the right side, bottom right side, that we can start to fill the results with inserting D into the empty set, and that results in the empty set itself and D alone in a set. And then we go up the stack. So we go up one level where we were about to insert C into each of the power set of D, and now we have that answer, so we can insert C. So we take the results, the preceding results, and we concat them to the new operation of inserting C into each of them. So we have D, we have C alone, we have the empty set, and we have the set with C and D. And so on up one other level, and you can see that we are multiplying by 2 the number of elements in the final results every time we go up one level, and we insert B into each of the power set of C and D. And finally, at the top, we are back at where we were. You might not probably be able to see all the sets at the top right, but you can imagine that there are all the combination of A, B, C, and D, all the subsets possible, and those are 2 to the power of n, and in this case 16. So we want to try to implement this, and the function that actually implements this is quite easy to follow, I think. So here at the top, the power set is taking the destructuring of a list or a sequence into the head and anything that is remaining. And if there is a head, then is asking for the power set of the remaining, as we were showing in the diagram. And the next operation is taking that subsets, the power set of the remaining, and is mapping, so is attaching or inserting into each of those subsets the head. When that is not happening, so we don't have a head, then we give the initial condition, which is an empty list of a list. So I already evaluated this down below, so we can see how it works. If we do the power set of, for example, A, B, C, D, we can see the 16 results as lists. It's easy to transform them into sets. We just need to map set. And if we count them, we can see they are, as expected, 2 to the power of 4, or 16. So we made a claim that this is going to be an expensive operation, and it is exponential. So let's have a look what happens. So let's try to do the power set of 10 elements, and it returns in about 2 seconds. And 20 elements, and it takes a little more. Oh, sorry, it was 2 milliseconds. Now we are to 1 second and something. And if we go 21, we can see that this is clearly increasing, and it is increasing in an exponential way. We could try more to go above the range, like above 21 elements, but at some point we will hit my local memory limits, so we'll stop here and show how we can improve this, or if we can improve this with Memoize. And this is also interesting because we are going to apply Memoize to a function that is recursive. And in order to do that, we define the memoization when we are defining the function itself. So the fn that you see here is the power set function, just without the name, and we memoize it right away. So when this recursive call of power set will happen, they will happen already on the memoized version. So if we do this, we'll get the memoized version of power set. Now let's see what happens. And if we try now to run the same power set twice, we'll see that it's really fast the second time, like order of magnitude faster the second time. For example, range 20 is evident. We get 3 seconds on the first attempt and 87 milliseconds on the second, and so on. But if we move on, like a range 21 or any other range, we see, or apparently, what is apparently, that we are not taking advantage of the previous memoization. So we are only taking advantage of the memoization if we are repeating the same operation twice. But if we move from range 20 to range 21, we see that roughly it's taking the same time, memoized or not. So let's check what's going on and see if we are using Memoize the right way. In order to do that, I'm just repeating here the same power set function, and I'm adding a print line just to see how the parameters power set is called with look like. And if we try now, for example, power set of ABC, we see that it's called with nil, with ABC, BC, and C. We add a letter to the bottom of this and another letter to the bottom of this, and we can see the repetition of this operation multiple times. But what we can see is that despite the fact that the letters are always the same except for the last one, and the combination of parameters power set is called with is always different. And this is because we are removing the first element and taking the rest. And every time we do this, we obtain a different list, and this different list is going to be a different key for Memoize. So the power set of 5 elements, where there is only the last one changing, is not taking advantage of the power set of 4 elements that just happened before, because those calls were never cached, because, as you can see here, the list of the arguments is different. So in order to take full advantage of Memoize, we're going to do a change to the power set function, where instead of destructuring the parameters with head and others, or head and remaining, we are taking everything but the last as the remaining, and the head is going to be the last. So this is a more expensive operation for lists, but what we hope is that since the exponential growth is so high that even after 20 or 30 parameters in the list, we are already going out of memory for other reasons, or like the computation is very long. It doesn't really matter, is not impacting that much if we access the last element of a list of 30 elements. So we are hoping that this change is not going to impact performance in a substantial way, or is not comparable to the gain of performance the Memoize is giving us. So if we evaluate this new function, we get the power set, and we can see how it works now. When we do power set of like an increasingly higher number of elements as input, we can see now that each time we call power set, the list of elements is different except for the last element, and this is creating compatible keys for Memoize. And finally, we can apply Memoize again, this time to the new version of the power set. And we got a typo, which is excess. I'm going to fix right away and reevaluate. And should be okay. And if we try again now, we're not printing anymore, but what we can see is more or less the same behavior when we hit power set twice with the same input parameters. We see an order of magnitude increase in performance. But what should happen is that when I do it with range 20, this range 20 is partially reusing all the computation that happened for 10 arguments as input. So if you remember the numbers that we saw before, this range, or you can go back in the screencast, you can see that this range of 21 is much faster now compared to what it was before, because it's taking advantage of all the previous computation. So I think the lesson to learn in this case is you need to know your key space and pay attention to that. If you just apply Memoize blindly, you can have surprises that you don't realize. All right. I hope you got an idea of how Memoize is useful and how it can be used. And I think this is all for this episode of the Closure Builds screencast. I hope to see you next time. And this GitHub repo at the bottom of the slide is the link to the show notes that contains the code that you saw today. So if you want to see the code at a slower pace, you're free to do so. And you're free also to inspect and verify the numbers yourself. And if there is anything that can be improved or any inaccuracies, please get in touch, post a comment on the YouTube website, or just get in touch through my Twitter handle @reborg. So thank you for listening. Until next time, goodbye.